All right, we have a ton of stuff to get through, so let's get to it. We're going to take a look at the free undamped vacuum, and we're going to look at a spring, the oscillating spring. This is the equation we're going to be looking at. We have the second derivative, and then we have the W naught squared, and here's the x, and that's equal to 0. We know that W naught squared is supposed to be equal to K over M, and this is supposed to be the natural resonant frequency. Natural resonant frequency. And we should be able to solve this equation, but what we're going to do is do a quick little replacement. So we're going to call this derivative here, we're going to call it r squared, and then this x, we're just going to get rid of it, and we're just going to look at the coefficient. So technically, we should put that on the other side so we can solve for r. And so we can see that we would get an imaginary square root here, because you're going to have to take the square root of this negative number in order to solve for r. So our answer is going to have i's in it. Some answers to this equation, so we have sort of like x1 is going to be equal to e to the I W naught t. Okay, that's going to be one possible situation. Remember that we have two answers to this, so we have an x2 is going to be equal to e to the negative I W naught t, and that is basically going to be the r term right there, I W naught, that was r. Well, this is nice, but let's remember that our answer should be including the superposition of both of these solutions. So let's go ahead and put some coefficients in front, and we're going to call it maybe a, and then we're going to have e to the I W naught t, then we're going to have to add an a star. This is the complex conjugates here, e to the negative I W naught t. The reason that these are going to be complex conjugates is because if you were to try to add this a plus bi over here, and then you want to add the a minus bi over here, then we would end up with a 2a, and this is actually going to be a real term. So the imaginary stuff goes away. Well, that's pretty nice, but it's still not a very friendly form. So let's try to convert e to the I wt. And we're going to want to convert that into sines and cosines. So we're going to say like cosine wt plus the I sine of wt. And we can also do that for the negative version. Let's just write that out over here. And that's going to be cosine of wt. And then we have minus I sine of wt. So when we convert these and then try to add it all together, we're going to get some other constants here. So we got a cosine of w naught t, and then we're going to have b plus b of the sine version of the w naught t. So we have some sort of intense algebra going on behind the scenes, but it simplifies over here to a and b. And if you wanted to find these coefficients right here, it's actually just going to require you to go to x naught. You can figure out what x is at 0. That's going to give you the amplitude. That's going to be a. Okay, and then you could also do the same thing for the derivative of x, the velocity at the initial point. And if you do that, then you're going to find you have to take the derivative of the position here, so you're going to get b w naught. This really crazy trig simplification we can do to essentially call this a c over here, and then we're going to put a cosine of w naught t, and then we're going to add in a phase angle right here. Okay, we're not going to get too into how we were able to do that, but let's realize that the c right here, this amplitude, is actually going to be the square root of a squared plus b squared, and I'm just going to replace this with xm over here, because that'll just realize this is the x max right here. It's the amplitude, and then we have this cosine with this phase angle. Well, let's figure out the phase angle. What we could do is we could take the tangent of the phase angle and set that equal to b over a, and that would be these coefficients here, and we can figure out all this stuff. Interesting. Well, that was for the free undamped vacuum, but let's go ahead and take a look at the damped homogeneous situation. We're going to change that original formula slightly. We're going to have, we're just going to put that coefficient of m back over here. Then we have this new thing over here. This is the damping force. Just introducing this term here, right? Damping force. And this is going to be in newtons, so all of these terms are supposed to be newtons. ma, this damping force here, which is a coefficient here. This is a coefficient. And this is going to be in kg divided by seconds. And then, of course, we have the kx, it's the spring constant. The equation of this force is going to be F equals negative b times the derivative of x, as you can see. And we could also set that equal to negative gamma mx. I'll go ahead and put gamma right here. Say gamma is equal to b over m. And the units here are going to be hertz. And this is called the decay rate. That's a little crazy, but what we can do is now we can divide everything by m, and so that we can get the second derivative of x here by itself. Then we have b over m, which is going to simplify to gamma. Put gamma here. And then we have the x derivative right here. And then we have k over m, which is going to be w naught squared. So put that. And then we still have the x, and that's going to be equal to 0. Now, if I wanted to solve this equation, it's going to be kind of similar to what we're doing over here. We're sort of going to assume a solution form. But the solution form is going to be xt equals c e to the alpha times time. Remember, in the previous equation, we were trying to solve for these r terms right here. So underline these are the r's. In this case, we called alpha the r's. So we're going to try to set up the quadratic equation for the alpha. And we're going to realize that it's just going to be this thing here. We kind of have like the alpha squared. And then we're going to have plus this gamma, and there's an alpha here. And then we have plus the w naught squared, and then get rid of that x, so that way we have this. This is going to be how we solve for alpha. And this is simply going to be just a quadratic equation. Okay, but I'm just going to sort of solve that real quick here and simplify it down sort of in the same step. So we're going to have the final result being a negative gamma over 2 plus or minus the square root. And then here we're going to have so gamma over 2 squared, gamma over 2 squared minus the w naught squared. Let's realize that we're going to have three situations that happen. If we try to damp this, we're going to either have an overdamp situation, which means we're not even going to ever get a single oscillation. So we're not even going to let that cross this x-axis over here. We're just going to make sure that this wave takes a really long time to finish. Or we could damp it critically, so we could essentially immediately and perfectly, just perfectly get that nice clean finish right down to 0, basically in one fell swoop, clean. Or we could underdamp this, in which case it's going to continue to cross that x-axis and essentially take a long time to finish oscillating here. Fill this in with a little line here. These three situations depend on the result of the square root over here and relationship between these two variables, the gamma and the w naught. So essentially, if gamma equals 2w naught, then this all goes away, and we're going to get two equal alphas. Two equal alpha, where the alpha is going to be equal to negative gamma over 2, right? Negative gamma over 2. And that's basically it. Of course, this is also equal to negative w naught, so let's just keep that in mind. Let's look at the overdamp situation, where this term is going to be much larger than this term. Then we're just going to end up with a positive square root. So we essentially get two real alphas here, two real alpha situations. And it's going to be the plus or the minus version, depending on the plus or the minus sign outside of the square root. Then we can go to the underdamp situation, and we'll find that this w naught term is much bigger than this term. So we have a negative square root, and well, then we're going to get two complex alphas. So this is actually the most important situation. So let's go and figure that out. We're going to have sort of, again, this negative gamma over 2 first. The alphas are. When we try to add this factor, here, the square root sign, we're going to simplify that to an IW1. And that's going to be the damped frequency. So let's go ahead and define that. W1 is going to be essentially this square root stuff a little bit backwards. We're going to have W naught squared minus the gamma squared. So gamma over 2 squared under the square root. That's going to be our damped W1. So let's try to figure out what the homogeneous X is going to be for the overdamped situation. It's going to be A e to the alpha plus, we'll put an alpha plus here, T, and then we're going to have plus the complex conjugate of e to the alpha negative over here. Alpha negative T. So that should be the answer for the solution here. It's going to be kind of difficult to expand this out and stuff, but that's going to be kind of a really complex answer. If you try to plug in, try to find the A, well, realize that x0 is going to be the sum of A plus A star. That will give us a real value because we're just adding complex conjugates again. Okay, and if we want to find x prime, now this is velocity, that will give us sort of this A alpha plus A star alpha minus. And it's kind of difficult to expand all that out, so just have to take it as it is. Let's just realize that there's going to be this sufficient time zone where as time starts to go forward, this exponential over here is going to decay so much faster than this one that this becomes the overbearing term over here. And so this amplitude can essentially be approximated by A e to the alpha plus t. And you can kind of get an approximate value here for sufficient times. However, let's be very clear that all three of these situations, the limit as t goes to infinity is definitely going to be equal to 0. Those things will always eventually turn into 0. For the critical situation, we have to deal with two equal alphas, so we're going to apply that recurring roots concept. We have xh is going to be equal to a e to the negative w naught t, but if we have an equal root, we're going to have a b times t e to the negative w naught t. So that'll deal with the recurring roots, two different coefficients there. If we want to find those coefficients, again, we're going to plug in x0, and that's going to straight up give us a. Not too bad. But if we plug in x naught prime there, that's the velocity, we're going to end up with negative w naught a plus b. Okay, and then this is essentially going to be the solution here for the critical. Got the overdamped, the critical, and now the underdamped. Well, for this underdamped situation, I'm going to go and define a new term here. I'm going to call this beta term. It's going to be equal to b divided by 2m. So it's essentially just y over 2 or gamma over 2. And this is also going to be in hertz. And this here is going to be called the damping frequency. Okay, decay rate and the damping frequency, they're kind of the same thing, just this is 1/2. That one's just going to help to simplify because then this here is essentially negative beta. So when we get our answer, we can write the xh is going to be equal to e to just plain old negative beta, just make things just a little bit simpler. And then we'll have a t. Okay, and then we're going to have this complex stuff over here. We're going to end up with some more complex conjugates. So we're going to have an a e to the iw1t. This is the damped frequency. And then we have plus the a star e to the negative iw1t. Okay, so this will leave us with the real version at the end. But of course, this is very nice. We can rewrite this. We're going to call e to the negative b. Here's the beta, the negative beta t. But now we're going to call this C1 cosine of W1t plus C2 sine of W1t. And again, we could do that just because we're expanding this sort of like we did before. We're reaching this conclusion again. But this time, there's just this e to the negative b term instead, where we didn't have that over here in the basic free undamped vacuum. So it's not like we're doing anything too crazy here. We just have this extra term. Now, if we wanted to find the C1 and the C2, all we have to do is just plug in x0. And we do that, we're going to find C1. And then if we plug in x prime, which is velocity again, we're actually going to get negative beta, negative beta C1 plus W1 C2. So you can kind of solve for those coefficients. But actually the most useful form of this answer is going to be xh is equal to, I'm just going to call this c, that would be c e to the negative beta, and then there's the t, negative beta t, this times cosine of W1t plus a phase angle, right? And this right here is going to, of course, be the amplitude right here. Well, let's say we want to find A and A star. What we could do is we could set A equal to the magnitude of A, and then we're going to have E to some phase angle here. Just realize that those two are kind of shifted by some angle. If you wanted to find A star, it would be the negative version here of the angle. But this is supposed to be also equal to, if you take just the real version, the positive version, then we're going to get C divided by 2 is also going to equal that A. And then we want to find the tangent of this phase angle. Just realize we kind of have to take C1 over that C2, and we should get that angle. So C2 divided by C1. Boom. So everything should be good there. If it wasn't clear, all this stuff right here is the amplitude. So that's going to be X naught right here. X naught. That's this right here. That's the amplitude. Same thing over here. We have A. It's going to be X naught. It's going to be X naught. Over here we have the A plus A star. So these are the three ways that we could find our amplitudes. Well, that was pretty nice, but let's realize that if we want to find the general solution, we have to take the homogeneous situation and then also add the particular solution. That's going to be something like xt is equal to xh plus xp. In order to get this particular solution here, we're going to need the driving force, Ft. So we're going to put that driving force right here. That's going to be like an impressed driving force. You can kind of think of this like if you have a rope and you can kind of continuously oscillate your arm up and down like this and cause vibrations in the rope. And that's a driving force right there. This is going to cause a particular solution as t goes off to infinity. We're going to only end up with just a particular, where the initial homogeneous situation, that's kind of just going to die away, as we're just going to be left with the particular solution after a long period of time. For the particular solution, we're going to assume that x takes the form of a cosine of WD, that's the driving frequency, times t, minus a phase angle. So this WD, the driving force, is just going to be this. We're going to call it driving, and I'll put it in green. This is going to be WD. Now, in order to solve this, again, we're going to have to take this particular thing here, take double derivatives, take one derivative, and then just plug it in here. Then we're going to have to rearrange this equation, and we're also simultaneously going to have to handle this sinusoid over here. So we're going to get this simplified equation. It looks a little bit like this, negative W driving squared. And we have the plus I of the gamma. Then we have the WD. We have the W naught squared. And this is supposed to be equal to F naught divided by, and this is going to be a blue 2. There's a 2 right here with the M. We'll figure out how we got the 2 in a second, but let's just realize that here, when we take the second derivative of this, we're just going to get this WD. There's a cosine over here. We were able to handle that in another way. Here, we're going to get all this, and then here, this just comes down and becomes W naught squared. Okay, now this A comes from there, of course, and in order to handle the sinusoid, let's realize we had this stuff going on the side over here. We'll call cosine of WT is supposed to be equal to e to the IWT plus e to the negative IWT. Divide that by, here's where the 2 comes from. Boom. And we also have that situation going on for sine, if we ever want to do that for sine, but it's just going to be sort of the minus version. E to the IWT minus e to the negative IWT, and then we can divide that by 2i. So 2i. Okay, so now we've handled the sinusoid, sort of simplified all this stuff down. Let's just realize we're also going to have the complex conjugate solution, A star, and then here we have a negative instead of the positive here, but everything else is essentially the same. Let's underline this term right here. We're going to call this Z. this stuff right here, this is Z star. Okay, and then what we could do is you could say that Z star Z, that's going to equal the magnitude of Z. And so that's also going to be equal to the square root of W naught squared minus the driving W squared plus gamma and then WD, square that. Boom. Now what we can do is we can actually figure out the delta over here. So we could say that tangent of delta is going to be equal to the gamma WD divided by W naught squared minus WD squared. And that comes from here. So we're able to find that delta. Well, let's simplify this a little so we can finally get XP. That's going to be equal to F naught Z star. And now on the bottom, we're going to have the 2. And then we have an M. And here's the magnitude of Z. That's because we're looking for amplitude, right? So we're going to pull this to the bottom side. But we don't really like that Z, so we're going to multiply it by Z star. We're going to have to do it on both sides, so we get the Z star on the top. That way we get the magnitude on the bottom, and we essentially found the amplitude here. But we can simplify this in one more step. We'll just call this F naught divided by, there's a MZ, and then we're going to throw in a cosine WD minus delta. And this right here is going to be the amplitude. We'll call this the driven damped amplitude in the steady state. And it turns out that this value here is actually constant no matter what. So it's always going to depend on F naught, which is given, this M, which is usually given here, the Z, which comes from this, and this is going to be a fixed amplitude for the entire time that it's been driven. So it's kind of interesting. Well, that makes sense because the driven amplitude's going to always be the same. It's the driven amplitude, right? The same. Well, we could keep going here because there's still a lot, but I feel like we've covered pretty much most of the important things. But there's one more situation that might be useful. If the driven frequency is actually equal to the resonant frequency, then we can calculate the amplitude at resonance to be equal to F naught divided by B W naught. And we can see here that B can't be 0. B can't be 0. Because if it's 0, then all of a sudden we have an infinite amplitude. So essentially what that's saying is that if we have a driving force, then we must have a damping force as well in order for this to be realistic. Otherwise, things are just going to not work out. So this is going to be called the driven resonance amplitude. All right, and so that should be pretty much everything we need to know about damping. Oh my God.